Hello folks, we are going to continue our discussion of atomic absorption spectroscopy from chapter 7. We left off talking about the different sources of broadening and doing the block diagram, the simple block diagram. We're now going to elaborate on those different types of sources as well as different types of sample introduction. So the first source we'll talk about is this hollow cathode lamp. That's what HCl stands for. This is one of those times where being remote just doesn't do it justice because I can't pass one around to show to you. But what we have here is we have this hollow cathode, as you can see, and that the interior of that metal cup is essentially what it is. The interior of that metal cup is lined with whatever atom of interest. And so the actual cathode is formed from the metal that we're interested in. Remember, AA is not great for nonmetals, and so, and this is the main reason, because we can't form a cathode of nitrogen, since nitrogen is a gas at room temperature, and at the temperatures required to generate these ions. Right? Unfortunately, in this diagram that's out of our textbook, the legend is all different colors, but the actual figure here all look the same to me. And so I'm going to just take a minute here and recolor them. Here we go. So, this lamp is in a glass envelope, just like all light bulbs, and it's filled with some inert gas, often argon. And what we do is that argon gets ionized, right? That's our green there. And when that argon's ionized and it's attracted to the cathode. Remember, cathodes are negatively charged. That argon becomes positively charged. And so it's attracted to that negatively charged cathode. That collision generates this target atom in the excited state. That's in our gold there. Once we have that atom in the excited state, based on that excited state lifetime, it's going to decay back down to the ground state. And so the metal atoms are excited, and when they relax, that's when they release that photon. So why use the metal of interest? Well, if we use a tungsten bulb, right, let's say that tungsten light bulb puts out light in a range from 300 to 900 nanometers, right? We've got 600 nanometers worth of light. Let's say that's 600,000 picometers. If we know that the bandwidth of our emission of interest, our transition of interest, is just 10 picometers, we're only using 10 out of 600,000 picometers of the bandwidth of that light source. So even if our molecule, even if our sample absorbed every last photon, it would only be absorbing 10 picometers out of the 600,000 picometers of bandwidth that light source is generating, and our detector would have to be incredibly precise in order to pick up on that difference. Even if we had a good monochromator where maybe we had a bandwidth of 3 nanometers, right? That's still 3,000 picometers. So 10 out of 3,000, even with a good monochromator, you're still looking at an incredibly small amount of light that could be absorbed. So we use a light source that's very specific for the element of interest. And so if we're measuring copper, we're going to have a copper cathode. If we're measuring zinc, we're going to have a zinc cathode, etc. One of the benefits of a hollow cathode lamp is that the cathode can be made of multiple metals. And so some of the lamps that we have in the lab are, 6 or 7 or 8 metals, because, as I mentioned in the previous lecture, it doesn't matter if we have this mixture, because each element is bound to have at least 1 or 2 specific emissions that we can use because there's no overlap in atomic spectra. Not there's no overlap, but there's very little overlap in atomic spectra. Okay? And so the cathode may be a mix of different metals. The higher the current that we use, so some drawbacks to HCl, the higher the current means that molecules, atoms, are going to be traveling faster. We talked last time about how molecules moving quickly can induce Doppler broadening. And so the higher the current, the more Doppler broadening we'll get. And another downside that comes along with that multiple metals is that you have a shorter lifespan overall, right? Let's say that you're mostly interested in copper, but you also want to look at zinc and manganese and lead, for example. Maybe you buy a lamp that has those elements in it. If your copper in that cathode may be depleted faster than if it were in a pure copper lamp. But the trade-off there is that you're able to analyze a broader range of metals. You don't have to spend $600 on 4 different lamps. You can spend $600 on one lamp and analyze more metals. And so it's that balance between cost and lifetime. Now, there is another variety of source. Unfortunately, we don't have this one at Wofford, and so I don't have one to show you, but this is a pretty good schematic. This is not from our textbook. But what you have is this is an enclosed cylinder, so you really can't see what's going on, even if I did have an example to show you. But what you have is you have a small lamp. It's got it has inside it a cathode that's made of the metal of interest. It's ionized by this ceramic holder here, and these blue coils of wire. There's an RF frequency, radio frequency, that's passed through them. That radio frequency causes the material inside the lamp to heat up and go into an excited state. Once it's in that excited state, again, depending on the lifetime, it will relax back down. And so the metal inside this lamp here, okay, this lamp has got to be made of quartz so the light can get out. That metal is heated by the RF coils. Right? So those radio frequency coils can heat up, and they'll heat up those metals when they're in a resonant frequency. And so that metal is heated by those RF coils into some excited state. And then it's just like a hollow cathode lamp. It will relax back down and emit that photon. Okay. Because we don't have to have enough, we don't have to apply electricity. And so a benefit of these EDLs is that they operate at lower current and therefore tend to have longer lifespans. Another benefit is that because all of the metal is sort of trapped inside this lamp, trapped inside this little quartz bulb here at the base of our EDL, is that the metals don't diffuse away. And so that also gives us a longer lifespan. EDL, sorry, I didn't mention that, is electrodeless discharge. So no electrode, is just heated by that by the RF coil. Right, there are some disadvantages, of course, as with everything. So one of the disadvantages is that these are more expensive. They're more expensive than the hollow cathode lamps because you have more quartz. There's more manufacturing that goes involved. There's more manufacturing that's involved in making this casing. And of course you have to have some source of RF energy. That radio frequency generator is not part of the AA instrumentation, and so you have to include that here in the base of the bulb, right? There has to be some RF generator. Also, the intensity of the emission is not as consistent. There's more power fluctuation than with a hollow cathode. Part of that's due to those RF coils, right? If you have any fluctuation at all in your input power, those RF coils are going to change in their energy output. That energy output changing can cause the power of the photons, the number of photons coming out, to change as well. And so we have lots of intensity fluctuation, more intensity fluctuation with EDL than with HCLs. Okay. All right, those are really the two types of sources that we might see. And now we have to talk about how we get that sample into the flame. Well, we don't just light it on fire, right? That's the number one thing to take away. We don't light it on fire. What we want to do is we want to make sure that it's well mixed. So just like when we do a solution-based experiment in UV-Vis, we put it in our volumetric flask and we invert it 20 times to make sure it's well mixed throughout that solution. We want to make sure that our analyte is well mixed throughout that flame. And so we're not getting 20% more at the beginning of the experiment than we do at the end. And so the way that we do that is by nebulizing. And so you see here, our sample starts off just in a beaker, and really it's almost too simple. You stick this little tiny capillary down into your beaker or your volumetric flask or your cuvette or whatever it is you have, and the pull of the fuel and the oxygen sort of create a vacuum. That vacuum draws up the liquid sample. And then that sample goes through what's called a nebulizer, right? And so the pull or the draw of the fuel and the oxygen gases causes the liquid sample to be drawn into the instrument. As it gets drawn into the instrument, it passes through a very fine pinhole, essentially, and that is what we call a nebulizer. This spray nebulizer. And so, again, if we're tracking this flow, we have our sample. It comes up this sample capillary into the chamber. And then by the time it's at this point, it's in this gas phase, right? We already have these droplets of sample. As it flows through this tube here between the sample inlet and the burner head, there are these. This instrument has two. The one we have just has a single. It's a little plastic piece. It's called a flow spoiler. And what it does is it essentially is a barrier. It's a stop. Anytime you have droplets of solvent, droplets of our solution where the solvent hasn't evaporated away, that flow spoiler will stop anything that's still in the liquid phase while allowing the air to flow around it. Right? All the solvent that evaporates after this nebulization is drained off into a waste container here. So then what gets to the burner head is a mix of the fuel, the oxidizer, or the oxygen gas, and our sample. That's what reaches the burner head. And so this spray nebulizer that we see here in this inset is the most common type, and it's the one that we have on our instrument. There is a different type called a Babington nebulizer. And this Babington nebulizer is good for two different types of solutions. This is good for very viscous solutions, as well as for solutions with a high ionic strength. Solutions with a high ionic strength are less likely to have all of the solvent evaporate off fast enough. And so you'll end up with a lot of solvent residue in your flame, and you may actually put out your flame if there's too much solvent, especially if it's a non-flammable solvent. And so the way that this Babington nebulizer works is that you have this sample on a slow continuous drip. And again, think about a viscous solution like honey. I mean, that's maybe too viscous, but something more like honey than like water. It's going to sit on top of this bulb and flow down the bulb towards this little hole. So there's one little hole in this glass bulb, and as the air comes in, now this says compressed air, right? But this is really this is going to be our oxidizing gas. Often that's air, but it doesn't have to be. Our oxidizing gas comes in, of course, goes out the only outlet, that little pinprick, and any sample that's sort of at the top of that pinprick is going to get aerosolized in that process. So we get to the flame. We're starting to get to the good stuff, right? A couple of things to keep in mind as we move into talking about the flame. What we want to measure, right, are not ions and not excited state atoms, right? Ideally, we will measure ground state atom. So we have to strike this balance between having a flame that's so hot and so intense that we just strip electrons off of it and we're making ions left and right. Right? We do not want ions or excited state atoms, and the reason is the wavelength that we're using is particular to that metal. If it's already in the excited state, it's not going to absorb that photon anymore. If it's an ion rather than the atom, it's going to have different sets of absorptions. And so we want ground state atoms rather than ions or excited state atoms. But at the same time, this balance that we have to strike is that the flame must be hot enough to completely atomize our molecule. And so it's a bit of a balancing act between, having it hot enough to break all of those covalent bonds that are in our molecule, but not hot enough that we're actually ionizing or exciting those atoms. And so if we take a look here, of course, if you've seen a Bunsen burner, there's that inner cone and then the outer cone of the flame. The flame in an AA is exactly the same. You're going to have this inner, smaller primary combustion zone, and that's hopefully where our atomization is occurring. And then outside of that, you're going to have a secondary combustion zone. Now those are the blue colored regions in this diagram, and in between those two is where we want to take our measurement. We want to take it in that interzonal region. And so you can see here the light from the HCl or from the EDL is shown as this sort of blue sun. Right? That's about where we want to take our measurement. Hopefully what's happened from the point of origin of the flame, right? Here we start with our molecule. So let's sort of draw this in. Here we have our molecule. Hopefully after this primary combustion zone, it's been atomized. Right? So no molecules anymore, only our elemental atoms. In your in this example here, they've sort of color-coded for us the difference between ions and excited state and ground state. And so if you can't see this very well, take a look in your textbook. This is figure 710. Take a look here. But there's a few analyte ions, right? We're going to ionize some of them. It's inevitable. We're going to excite some of them. It's inevitable, right? We have a flame that's hot enough to burn, to atomize things. It's just that balancing act of what fraction are we actually atomizing versus exciting. Hopefully you get to some point, right? So let me add in here. This has been atomized up here somewhere, right? Things start to cool down. Excited atoms start to relax. And so at this point, right, they're making their own photons. And so we don't want those photons to reach the detector. And so that's, again, part of why we position the flame where it is. So that by the time we're at our radiant light source, by the time we're at that optical path, we have only ground state atoms. Again, ideally, this is an ideal situation. If we've got 100,000 atoms, we're bound to have a few that are either ions or in the excited state, but hopefully we've chosen a flame temperature where most of them stay in the ground state, or at least cool down to the ground state by the time we get to that interzonal region. All right. So, controlling the temperature. Right? One of the ways that we can sort of modulate temperature is by choosing a different fuel oxidizer combo. And so in this table, the acetylene and the natural gas, right, these two are fuel options. And then these three are our oxidizer options. The most usual situation is an acetylene-air mixture, and you can see that burns at around 2300 Celsius. But we're going to choose this based on the Boltzmann distribution. Now, we didn't talk a whole lot about the Boltzmann distribution. It's part of Chapter 2, but we're gonna bring it up now. Essentially, what the Boltzmann distribution is for us is it tells us how many atoms, particles, nuclei, we're going to talk about it in terms of lots of different things, but how many atoms, in this case, are in the excited state versus the ground state at a given temperature and a given energy of excitation. So this Boltzmann distribution tells us the number in the excited state divided by the number in the ground state, that ratio, is equal to the degeneracy is given the symbol lowercase g. The degeneracy of the ground state, excited state, divided by the degeneracy of the ground state, G sub g. All that is times E raised to the negative delta E, so the energy of that transition, divided by Boltzmann's constant times the temperature. This Boltzmann's constant, 1.38 times 10 to the negative 23rd joules per Kelvin. Of course, so our temperature must be in Kelvin, and our delta E here must be in joules. Of course, remember that delta E is the same as the energy of our photon. That's the energy of the transition we're interested in. By and large, if the degeneracies are not given to you, you can assume that these degeneracies are 1 if they're not given. One of the homework problems from Chapter 7 takes you through this Boltzmann distribution to figure out sort of what fraction of the atoms are in the excited state for a given flame temperature. We always want the hottest flame while keeping the smallest number, that smallest ratio of excited state atoms. So we're sure we're atomizing everything. We're sure we're completely using all of the sample, but we're not leaving any atoms in the excited state by the time we measure. And so look out for that homework problem. Okay. All right, now there is another kind of AA aside from the flame AA, which is what we have at Wofford. It's a graphite furnace AA, and so GFAS AAS. And what we have here, if you look at it, instead of a flame, you have this graphite tube. So if you want to imagine an enormous pencil with holes at both ends, that's essentially kind of what it looks like. This diameter here is on the order of 1 to 2 centimeters, and so it's not enormous, but it's a pretty fat piece of graphite, pretty fat tube of graphite. And the way it works is you flood this tube with argon or some other inert gas so that your sample doesn't burn, right? We don't want the sample to burn and become CO2 and water and a little bit of other things. We really want it to atomize. We want it to do just like it would in a flame, and so we make sure that there's not a lot of oxygen in that system. We have argon in there to encourage the atomization. Right. Notice we have these 2 windows on either side. If we were using UV wavelengths, of course, we'd have to make sure those were quartz. But if we're not using UV wavelengths, those could be optical glass. There's a small sample port on top, and this platform that's in the middle of the graphite tube, that's shown here. And we have this small sample volume, so it's a liquid sample, and it can be a very small sample, right? One of the benefits of the graphite furnace is that this can be as small as 10 microliters. Usually when we talk about flame AA, we're talking about a minimum of a milliliter. Because so much of it is goes to waste, that solvent doesn't evaporate. We need at least a milliliter of solution for flame AA, but we're talking about as small as 10 microliters, probably normally on the order of 100 microliters per analysis. So this is then heated in stages. And so these stages, first we heat it to about 800 degrees, and that removes any water and other solvents that we might have. The second stage, we're going to take it up to about 1300 degrees. And what we're doing at this stage is we're breaking down a lot of those organics. We call this ashing. And that breaks down organics. The third step takes us up to 2000 degrees or more. And by heating this pretty quickly, what actually happens is that as that surface, that platform, that graphite platform heats up quickly, we'll actually get this little plume, almost like this little explosion of material. Right? Plume of gas phase. So think about it almost like a little volcano, right? Eventually we get to some point where that material just goes into the gas phase, and it creates this little, as it expands from solid to gas, it just creates this little explosion, this little plume of material, and that's when we analyze. Because that argon is flowing through the tube, we don't have a long period of time for that analysis to occur. And so, whereas with flame AA, you might be able to average over 3 or 4 or 5 seconds. That's one of the reasons why it takes a milliliter of sample. In graphite furnace AA, you are going to have to, if you want to take averages, you're actually going to have to inject different samples into the furnace rather than just having a continuous flow and being able to average over time. The last step in this heating cycle is we heat it up to white hot. So you've seen your burners at home get red hot, right? This heats to white hot. And the real purpose of that is just to burn off any leftover residue. Make sure everything that's in there is in the gas phase, and essentially prepare the furnace for the next sample. Now this furnace, like I said, is small, a centimeter or two across, maybe 10 centimeters long. It doesn't have a lot of thermal mass, and so it heats up and cools down relatively quickly, but you're talking about, on the order of 5 minutes per sample. Maybe a little bit less. Let's say 3 to 5 minutes per sample for you to do this. And so if you need to run things in triplicate, right, it's going to take you at least 10 minutes to get your samples done. Right? Where if you need to run something in triplicate for flame, it's not going to take you nearly as long. The argon, again, helps with the cooling down of that furnace after you're done burning off the residue, and it prevents that graphite from being part of the sample. Right, the argon helps the graphite from being oxidized on the interior, and sort of maintains the structural integrity of that graphite. All right, so how do we actually measure AA signal? What are we doing? Well, a couple things to keep in mind. First, for a flame AA, we can get down to about, as I said, 0.1 part per billion, so 100 parts per trillion, and you can expect to pay about $25,000 for that instrument. In the graphite furnace AA, we can increase our sensitivity by a factor of 10, so 0.01 ppb, right? That's 10 parts per trillion, which is really quite low. Right? And for some elements, you might get even lower than that, but you're talking about double the cost, right? You're talking about $50,000 to $60,000, and so it just goes to show how much we can actually detect. What do you need? What's it going to cost you? One of the drawbacks of the graphite furnace, right, is that if you have very concentrated samples, it's not going to work very well. And so this isn't great above, say, 10 parts per billion. Right? The reason being, we have that sample in that small container, and remember that measurement is so quick because that plume doesn't last forever. That argon sweeps through and clears it out. Because that sample size is so small to begin with, and our measurement time is so short, if we have a whole lot of sample, we're gonna hit that limit of linearity real quick, right? We're gonna get to that nonlinear part of Beer's law with a pretty low concentration, actually. Flame AA, you can take this up to 10 parts per million, right? And so this has an incredible dynamic range. There's a good vocab word for us, and it's a cheaper instrument. So unless you really need to get down to that 10 parts per trillion, Flame AA is a very useful tool. When we think about AA, of course, we're going to use Beer's law, but the power from the detector, doing a background subtraction in AA can be pretty intricate, right? And so the power that reaches the detector, I'll say that's the net power or the total power. Right? That's equal to the initial power from our light source minus whatever power is actually absorbed by our sample, plus any light that is outside the bandwidth of our sample, but within the bandwidth of our monochromator. We also have scatter, right? We lose some light to scatter, but we also gain light from the excited atoms that are in the flame. And so we have the power from those. But then we also lose light from absorption of other species. And so that's background absorption. Whew, look at this, 6 different terms. Again, I'll go through these. Our overall power. This is the initial power of the source. We're going to subtract out the actual intensity, what's absorbed by the sample, or the reference, right? If we're talking about taking a blank measurement, this could be the amount absorbed by the blank. We gain a little bit of power that's outside the bandwidth of our measurement, right? The P without any subscript, that power is only absorbed in that small bandwidth where the atom will actually absorb it. This P sub L is light that's outside the bandwidth of the analyte, the transition that we're interested, but within the bandwidth of our monochromator. I'm going to put delta lambda for bandwidth of monochromator. Right, so remember we talked about these transitions have bandwidths of 10 picometers, 50 picometers max. And we can make really good monochromators these days, right? We can make monochromators that have 100 picometer bandwidth. They're expensive and they're not on the cheap end of AA equipment, but we can make them. And even with a standard monochromator at half a nanometer is reasonable. If we're at half a nanometer and the bandwidth of our transition is 50 picometers, then we're talking about 90% of the light that's getting through our monochromator is not light that we really care about. And so that's a big source of extra light in our equipment. Think about this as stray light in a UV vis. This P sub S, right? This is power that we lose to scattering. Again, while we want to atomize everything that's in that sample, sometimes we don't, and we end up with little pieces of soot. Right? Think about any fire. You end up with little pieces of soot, uncombusted materials. And those uncombusted materials are going to not absorb light, but rather scatter it. And so if a photon that we're interested in, a photon of the right wavelength, if it happens to hit one of these solid particles, it's going to be scattered off in a random direction rather than transmit through to the detector. This P sub F is extra intensity, extra power that we get from the flame. And so our flame, right, has light. Our flame emits a color even when there's no sample in it. And so the flame will emit our wavelength of interest, at least to some small degree. And so you have to take that into account. That's one of the easier ones to take into account. This PB is background absorption. And this background absorption is, again, if we have molecules that have not been fully atomized, then they can absorb. Remember, molecular absorptions are very broad, right? So if they haven't formed soot, if they haven't been converted into soot, and they're still left in their molecular form, they could absorb light in the same range as the element that we're interested in. And so again, we can balance some of these things out by choosing a good temperature for our flame, making sure that we atomize completely. The more we atomize, the more we burn, the less background absorption we'll get, the less scatter we'll get due to soot. And so, sort of setting up our experiment correctly and well will help us along. And so we have to take a lot of this into account, but it's not as bad as it may seem. Well, that's the end of Chapter 7. If you have any questions on this, feel free to shoot me an email, or you can schedule an appointment on Appointify. That's on our Moodle page. All right? Take care.